all the dignitaries present here and all the participants. A warm welcome to all of you. I, Dr. Mamta Thakur, Assistant Professor, Department of Mathematics, welcome you all to this ATAL Academy sponsored online FDP on quantum computing. I take the privilege in inviting dignitaries on the online platform. I request Dr. Suresh Paboju sir, Director IQAC CBIT to join us. Sir, can
Thank you,
you
madam. Thank you, madam.
Thank you, sir. Now I request Dr. P. Ravindra, Head Director of Smart Research Center of Life Sciences CBIT to join us. Please, sir.
Thank you very much, Dr. Mamata,
Thank you, sir.
for inviting me.
Thank you, sir. Now I request our HOD, sir, Dr. P. Raj Reddy, who is the coordinator of this FDP, to grace the occasion. Now I take, so ma'am, we are even expecting the chief guest of today's session, Dr. T. Shobharani from Hyderabad Central University to join us. She will be joining in a while. Please excuse us. Now, let us begin the program with an invocation song. Can we have Jaya from CSC 3 for the song? Good morning, Jaya. Please start.
ಶ್ರೀಕಾರ ಸಾಕಾರ ಸಂಜಾತ ಗಣಪತಿ ಅಂದಿಂತು ಮಾತೊಲಿ ನಮ ಸ್ಕೃತಿ ಓಂಕಾರ ಡಂಕಾರ ಸಾರೂಪ್ಯ ಗಣಪತಿ ಅಂದಿಂಚು ನವರಸ ಮಯ ಕೃತಿ ప్రభాత సమయాన ప్రార్థింతు ప్రముఖంగ ప్రారబ్ధముల బాపి ప్రహ్లాదమీయరా ప్రస్తుతించెద నిన్ను ప్రసాద గుణముతో ప్రాణికోటిని గాచి ప్రాభవం పీయరా శ్రీకార సాకార సంజాత గణపతి అందింతు మా తొలి నమస్కృతి ఓంకార డంకార సారూప్య గణపతి అందించు నవరసమయ కృతి అందించు నవరసమయ కృతి అందించు నవరసమయ కృతి. Thank you.
Thank you. Thank you. Ma'am, I take extreme pleasure in inviting you. Ma'am is here, T. Shobharani ma'am. Ma'am, I take extreme pleasure in inviting you in today's session as chief guest. Please join us, ma'am. Yeah. Now I request Dr. Suresh Paboju sir, Director IQAC, to deliver the welcome address. Let me take this opportunity to introduce him to you all. Dr. Suresh Paboju has been working as Professor of Information Technology at CBIT Hyderabad. Presently, he is also Director of IQAC and Advisor for Alumni Activities in CBIT. He has more than 30 years of experience and has more than 100 research publications. He has guided 6 PhD students. His research areas are image processing and computer vision, data mining, cloud security, software engineering, and many. Sir, we are blessed to have you here. Please address the gathering.
Thank you, madam. A very good morning to all of you.
Good morning, sir.
Good morning, madam. Good morning, sir. Respected Dr. T. Shobharani, madam, from School of Computers and Information Sciences, Hyderabad Central University, chief guest of today's function and keynote speaker. And respected Professor P. Ravindra Garu, Director, Smart Research Center of Life Sciences and Head Department of Chemical Engineering, CBIT. Professor P. Raj Reddy Garu, Head Department of Mathematics and Coordinator of this FDP. Directors, Joint Directors, Heads of Departments, and my dear colleagues, organizers and volunteers, and faculty participants from various colleges and universities from all over the country, and other distinguished invitees. A very good morning, and I welcome you all to this inaugural function of 1 week online ATAL FDP program on quantum computing, sponsored by ATAL Academy of AICTE. So at the outset, I feel privileged to speak in the function on behalf of our Honorable Principal, Dr. GPS Verma Garu, and congratulate Professor P. Raj Reddy Garu and his team and the Mathematics Department for organizing this FDP. So for the benefit of participants, and guest, I will brief about CBIT. CBIT was established in the year 1979 by the Chaitanya Bharati Education Society with three UG programs and 200 intake. The Chaitanya Bharati Education Society was formed by 13 distinguished eminent personalities from different fields of engineering, medicine, agriculture, law, industry, and business. Now, CBIT is offering 11 PG programs and 10 PG programs with an intake of 1,556. AICD approved 3 UG programs and 1 PG program in the thrust area from this academic year. So these programs include BE Artificial Intelligence and Machine Learning, BE Internet of Things, Cyber Security, including blockchain, then BE Artificial Intelligence and Data Science, and MTech Artificial Intelligence and Data Science. And UGC sanctioned permission to run 4 skill-based certification programs from this academic year 2021. The vision of the institute is to be a center of excellence in technical education and research. Our mission is to address emerging needs through quality technical education and advanced research. So we take pride in imparting functional knowledge that can ignite positive change and transform personal life and the society in economic, social, cultural, and intellectual dimensions. So in CBIT, 8 UG and 3 PG programs are accredited by NBA. Our institute has been accredited by NAC with A grade for 5 years. CBIT has become autonomous under UGC with effect from 2013-14, and the autonomous status has been extended up to 2023 to 24. So CBIT is an ISO 9001-2015 certified institution. CBIT secured 124th place in the top 200 engineering institutions in India, including IITs, NITs, as per NIRF rankings, and first among private engineering colleges in the state of Telangana. CBIT ranked first among the top private engineering institutions in Telangana as per the survey conducted by the Times among the engineering institutions 2020. CBIT ranked 14th among the top 100 private engineering institutions in India as per the survey conducted by the Education World India. So CBIT ranked 41st out of top 100 engineering colleges in the country, including IITs and NITs, and first in Telangana state, and 30th among the top private engineering colleges in India, and 9th among the top private engineering colleges in South Zone as per the survey conducted by the Week magazine, August 2020 edition. CBIT campus is spread across 50.8 acres with 5,000 plus students in the campus. So we have 519 committed staff, out of which 288 are teaching. 127 faculty possesses PhD and 115 are pursuing PhD. The state-of-the-art laboratories, excellent library, and sports facilities are available in CBIT. So artificial heart project and R&D block, Hexagon Capability Center, projects from various agencies like AICT, DST, DRDO, DMRL, ISRO, etc. are in progress. And a total of rupees 1 crore 3 lakhs 70,286 worth of ongoing sponsored projects are being sanctioned from the different funding agencies. Consultancy activities of worth 9 lakhs 95,000 is performed, and 10 training programs worth 36 lakhs 867 are organized during this academic year. CBIT has been recognized as a host institute for the implementation of the scheme, support for entrepreneurial and managerial development of MSMEs through incubator by the Office of the Development Commissioner MSME, Ministry of MSME, Government of India. So CBIT has established MSME Incubation Center in the year 2019 and is in the final process of getting approval from Niti Aayog for ATAL Community Innovation Center ACIC. The institute will receive a grant in aid of 2.5 crores towards capital and operational expenditure. The institute has to invest a matching amount for undertaking the projects under ACIC spread over a period of 5 years. Under ACIC, we have the plan to establish and incubate 100 startups in the next 5 years. The ACIC at CBIT will offer opportunities for community-oriented approach for everyone to innovate, ideate, and design impactful solutions for the society. CBIT is recognized as a member of National Rural Entrepreneurship Mission by Mahatma Gandhi National Council of Rural Education, Ministry of Education, Government of India, for imparting training with a mission of inculcating entrepreneurship among the students. CBIT is recognized and has been granted authorization by the US Council to offer US Council training courses and is an approved US Council authorized training center. Established CBIT established an Institute Innovation Council, and many activities are organized under IIC. So CBIT has initiated some of the startup activities in the area of Internet of Things, remote monitoring of electrical and mechanical equipment, GPS tracking system, cyber security, etc. So we are in discussion with the MSMEs and CBIT's alumni for initiating further startups and idea incubators. CBIT has partnered with the T-Hub's Pan-India initiative that envisions promoting and uh, support innovation and entrepreneurship among students, thereby creating wealth, strengthening the economy, and establishing sustainable employment opportunities in India. CBIT is training 50 students under the T-Hub's T-Tribe Launchpad program for the academia to inculcate entrepreneurship culture. So this is very brief about CBIT for the benefit of participants. So this FDP is planned with experienced resource persons, both from the reputed industries and academic institutions. The sessions include theory as well as hands-on. I request all the participants to involve and interact actively and keep the sessions alive. I hope and wish that the 5-day program will be fruitful and definitely enhance your knowledge and skills in the area of quantum computing. I also request all the participants to give a constructive feedback at the end of each and every session so as to enhance the quality further in the future programs. So uh, I thank all the faculty participants for being part of this FDP and making it a grand success. So without participants, and so it's not possible to conduct such programs. So I express my sincere gratitude to respected Kavikiriti Bala Saraswati Vidyabhushan, Dr. V. Balakunda Reddy Garu, our beloved President of CBIT, Founder Secretary and Correspondent of CBS, and Founder Principal of CBIT, and other honorable members of CBIT management, and our beloved Principal Dr. G.P. Sardivarma Garu for giving me this opportunity. I wish you all the best, and I hope you enjoy and you learn many things with respect to the quantum computing in all the coming 5 days. So I wish you all the best. I thank you and thank you one and all. I also thank the organizers for giving me this opportunity. Thank you very much.
Thank you, sir, for an insightful and encouraging talk. Really, it's very inspiring to hear you, sir. Thank you.
Thank
Now
you.
I request Dr. Ravindra Pogaku, sir, Head Director of Smart Research Center of Life Sciences, CBIT, to address the gathering.
Okay. Thank you, Dr. Mamata.
Sir, can I take a privilege of introducing you? Yes.
Yes,
Give me.
please.
Yeah. Dr. Ravindra Pogaku is a head professor of chemical engineering, director of Smart Research Center of Life Sciences. He has been very active in inculcating the concept of research in CBIT. He has a vast experience, which include more than 200 research publications and 4 patents. He is bestowed with the Distinguished Chemical Engineering Award from Indian Institute of Chemical Engineering, India, and we have much to. I think, sir, this time will not be sufficient to go on reading about your profile. We are blessed to have you, sir. Please grace the occasion.
Thank you. Thank you, Madam Mamata. Thank you once again for nice words about me. Good morning, ladies and gentlemen, and my respects to all the dignitaries. and also all the participants. At the outset, let me congratulate the Department of Mathematics for organizing faculty development program on quantum computing. It is very pertinent topic to enhance computational skills on quantum computing. I believe mathematics is the language of an engineer, but in today's world, computational skills is the language of everyone. I request Head of the Department of Mathematics, Dr. Raja Reddy Garu, and his team to conduct sequel of quantum computing in future for the benefit of academic and research faculty. Let me inform everyone in the Department of Mathematics is one of the 7 stars of the Smart Research Center of Life Sciences. It is doing good work, and I appeal to the remaining 6 stars of the Smart Center to conduct FDP programs on cutting edge technologies in near future. On behalf of the Smart Research Center, I am grateful to the management, the principal, for inspiring us to do such innovative activities. I thank Dr. Raja Reddy, HOD, for giving me an opportunity to address the participants. I wish AICT Training and Learning Academy sponsored online faculty development program to be a grand success. Thank you, one and all. God bless all. Thank you.
Thank you very much, sir.
Thank you, sir. Thank you. Now I request Dr. P. Raj Reddy, sir, head and coordinator of this program, to throw some light on this FDP and its multidimensional scope in various disciplines. Over to you, sir.
So, good morning, one and all. Good morning, one and all.
Good morning, sir.
Respected Chairman, Secretary, and board members, and today's Chief Guest of the function, Dr. T. Shobha Rani, Professor, School of Computer Science and Information, Hyderabad Central University. Madam, I am very thankful to you for accepting our invitation as the Chief Guest of the function and keynote address. Dr. J.P. Saradi Verma Garu, Principal, due to preoccupied work today is unable to come to this program. So I am very thankful to the Director, Suresh Pabboji Garu, IQSC, kindly accepted the invitation for this program. With his continuous support and guidance, we are able to organize this FDP, even though during the pandemic of this time. Dr. Ravindra Garu, Head of the Department of Chemical and Director, Smart Center for Smart is a director for this is all sciences,
Yes, sir.
Smart Center and Sciences. I am very thankful to you, sir, for attending this program. Then I come to the about the department. Department of Mathematics consists of 12 staff members. 11 out of 12 members possess PhD degrees in various fields as a fluid mechanics, number theory, operation research, and fixed point theory. So far, Department of Mathematics had published 200 papers at national and international level, organized 7 FDPs, 5 national conferences, and 10 webinars. Then come to about the FDP. It is highly interdisciplinary by nature, encompassing aspects of different engineering fields and sciences. A lot of research is going on quantum computing with world-renowned institutions, MIT, Stanford, etc. With help of the Microsoft, IBM, Regate, and D-Wave companies. The aim of the quantum computing is the processor performs multiple operations as an input in the form of superposable and outcomes its exponential order with less time. The purpose of the quantum computing is it is entirely different. This is another 5-10 years. It is a new revolution for all the computer science branches. Finally, I thank all the resource persons who have accepted to deliver the lecture. I hope all participants will enrich with the knowledge and share the same to the colleagues and students after the completion of ATAL FDP. Finally, I am thankful to AICT for facilitating FDP and quantum computing. Thank you once again for all. Jai Hind.
Thank you, sir, for an elaborated talk. Now I take immense pleasure in inviting the chief guest of today's inaugural session, Dr. T. Shobharani, Associate Professor from University of Hyderabad.
Thank you, madam.
Ma'am, give me an opportunity to introduce you. Ma'am received her doctorate on machine learning in bioinformatics. Her other areas of interest include pattern recognition, bioinformatics, and advanced data structures. Her latest research is on data reduction methods for imbalanced data sets, early detection of Alzheimer's using machine learning, etc. We are privileged to have you, ma'am. Please grace the occasion.
Thank you.
You
So,
can address this, ma'am. Yeah.
I can start the presentation.
Ma'am, it will be a small introductory talk, and after the closing of inaugural ceremony, we'll go with the keynote talk.
Okay,
Speak.
sure. No.
Yes. Yeah. You can give the introductory talks, ma'am, a few lines.
Oh, okay.
Thank
So, thank you very much for the invitation. So, it's nice to interact with you people. Quantum computing, as such, is another kind of paradigm we can say in the world of computing. So, we are used to the serial nature of the computing so far. So, unless we can think about different kinds of paradigms, there is no way you can actually achieve much more efficiency in computing. So this quantum computing is likely to help in that direction. So that's what we are going to look at, the theoretical aspects, and as well as already said, a hands-on experience about this computing in this particular program. So I hope the participants are going to benefit immensely from this interaction.
Thank you, ma'am. Hope we will learn a lot and keep up to the expectations. Thank you, ma'am. And now I take the privilege of delivering the vote of thanks. Ma'am, there is a little resound from your side, ma'am. Yeah, thank you, ma'am. A warm and cherished morning to all the honorable chief guests, directors. Principal sir is not available here because of some prior requirements. I include the respect to principal sir, directors, all HODs, and all the dignitaries, and above all the participants, a warm welcome. It is my privilege to propose a vote of thanks and acknowledge the contribution of all those who have worked hard to make this inaugural a successful one. I thank our management, principal sir, and the directors for guiding us and encouraging us to take a step put a step forth. I extend my sincere gratitude towards our HOD sir for his untiring efforts in conducting this FDP. Last but not the least, I extend my thank to the coordinators of this event, Dr. Suresh, and co-coordinators of this event, Dr. Suresh and Mr. Shrikant from CSC department, right from the planning to the execution of this, organizing and execution of this FDP program. On behalf of the CBIT family, I thank one and all for attending this session and making it a successful one. Thank you.
Madam, real photograph, madam.
Yes, I request all the people to please switch on their cameras so we can have a photo. I mean, we will take a snapshot of this, screenshot of this. All the dignitaries and all the participants also. Suresh sir, are you taking the pic?
Okay, madam.
Thank you.
1 minute, 1 minute. Functions, the screens. ఒక్క నిమిషం ఒక రెండు
Sir,
మూడు
there is
ఫోటోలు
very sound sir from your side.
శ్రీకాంత్ సార్
వేరేలా కొట్టాలన్నాడు కదా ఇది వచ్చేసిందా ఓకేనా సార్ ఇస్ ఇట్ ఓకే మేడం కంటిన్యూ మేడం Mute.
I'm sorry. Now I request Shobharani ma'am to start with the keynote address, and we are going to have the first talk of the day.
Yeah, thank you very much.
You can start the screen sharing also, ma'am.
Yeah.
I request all the participants stay back and have a keynote address by Dr. T. Shovarani madam.
I request few participants. I think there is some background noise. Please mute yourself.
So, I think it's visible.
Yes, ma'am. It's clear.
Sure. So, okay. Once again, thank you very much for the invitation. And today, in this talk, I'm touching some points regarding the basics and then some rudimentary things. But anyway, in the FDP program, we are going to cover in detail lot of things in this lecture that I have given. So, first of all, I don't know whether all the participants are aware of the computer science things. So, little bit introduction about that. So, what are the powers of a computer model or a classical computer model? So, we have abstract models that is given by Turing and then Gödel and so on and so forth. So, what are the powers of these models? Can they be used to solve every problem in the world? right? So that's the first question. So then comes the answer that, yeah, unless you have a certain way of solving a problem, you will not be able to construct a method to solve the problem and convert that method into machine codable thing, right? So then comes, if a particular problem has no method, then there is no way you can solve that method. So that's the limitation of our classical models. So classical models then can be limited by, can be limited in two ways. So the first one is limitations of the classical computer models is that these kind of problems where there is no solution at all cannot be solved, right? There are lots of such problems existing, and then even if the problems are solvable, right? So you know the method how to solve the problem, then still if the problem is going to take enormous amount of time, then there is no way that we can solve the problem, right? So these kind of problems that are solvable but take huge amount of time, we call them as NP, right? So then again, you can have NP complete, NP third, and so on categories in those kind of uh, problems that we can solve, right? So then the problems usually that are solvable that have huge amount of time or takes huge amount of time, they are called to be having exponential time complexity, right? So let us say if we are having a problem which takes, let us say, some thousands of years of time, there is no point in actually then trying to wait for that solution, right? Obviously you will not wait such a long time. Even factor of seconds is also sometimes looks a very long time, right? When you are searching for something. So then obviously these kind of solutions for a problem, then there are going to be a limitation here, right? So then comes, if we can actually now parallelize, right? So instead of waiting exponential time, if you can actually parallelize this problem and try to find solutions and then pick up the best solution. Usually the optimization problems have this kind of nature. So which is the best solution given the problem? So you may have lots of solutions, but you want to pick the best solution out of the given solutions. Then how do we actually get this kind of solution, right? So if even then if there are exponential time complexity solutions, then that also is not going to be giving, that also is not going to give you a best solution in what you call polynomial time, right? So then how do we actually solve this kind of problem, right? So one problem comes from the serial nature, right? So a paradigm that works in parallel is what we would like to get, right? So the other direction is the limitation of the physical systems, right? So you you we all know about the history of computing, right? So when the initially when the computers were constructed, I think it's almost a room size computer that was constructed. So then it actually started, we started developing the transistors. The transistor size has become small and small. So we all know about the Moore law. 1965 proposed that every 18 months the size of the, or the computing power doubles, right? So the computing power doubles because we are able to pack in more and more number of transistors into the area, whatever is the area of the uh, system that we have, right? So then as we start packing in more and more transistors, which actually improves the performance or power of the computers, then comes the limitation that when we actually reach the size, very small size, which is on the atomic scale, then there is a problem, right? So here I think Pentium i9 chip actually consists of some, if I remember it correctly, 1.7 billion transistors, right? So there's a huge amount of number of transistors that you have on the chip. So now, as you try to reduce the size more and more, as the size approaches the atomic scale, then there is a possibility, or there is a probability that the what do you call the conduction across the transistors is possible, that may actually corrupt the signals, right? So they'll reach a very small size, so then it is going to be a problem, right? So then we are now right now kind of handicapped with both of these limitations. One is the size and the other is the complexity and serial nature of the computing. So as I was saying, as the size becomes more and more less, then the electrons tunnel through the microthin barriers between the wires, corrupting the signals, right? So there is no problem. We can try to put them in the chip, but the problem is that the tunneling may happen and then it will correct the signals. So then comes the question, how do we actually improve the computational power? Right? So in what direction we have to move so that we can improve, we can overcome these limitations. So it was proposed around in 1982, right? So in 1982, if we look at the brief history here, Feynman was the one of the few who attempted to provide conceptually a new kind of computer, right? He was the one to come up with a new paradigm, which actually is using the principles of quantum physics, right? He constructed an abstract model to show how quantum system could be used to do computation and also explain how such a machine could be. So the laws that are governing the classical physics, right? They are no longer upheld in the when you go to the atomic level, right? Electrons, protons, atomic levels. The laws that govern the microscopic governs the microscope level, governs at the microscope level is the quantum laws, right? So then these are the ones that could be used actually to come up with a new kind of computation. So that was proposed by Feynman. Then in 1985, Des realized this Feynman ascension, and he eventually led to a general purpose quantum computing, right? So he actually kind of showed that these principles could be used to build a quantum computer. Then P.Suresh is one who has actually proposed an algorithm using the quantum computers to crack an important problem in number theory that is called factorization, right? So how actually this particular algorithm could be used on a quantum computer, that's what he has proposed, right? So he showed an ensemble of mathematical operations designed specifically for a quantum computer, and to make such a computer to factor huge numbers extremely rapidly, right? So as we were saying, quantum computers then require a special kind of laws in order to realize this kind of quantum computers. So quantum computing is essentially using the laws of quantum mechanics to process the information. Then quantum computing is the use of quantum phenomena such as superposition and entanglement to perform computation. Right? So they are using these two laws, superposition and entanglement, to perform the quantum computation. Right? So computers that perform quantum computation, they are known as quantum computers. Right? So there is a proposition, and there is actually a kind of rudimentary way of working with this proposition has been proposed. Right? So using this superposition and entanglement, quantum computer can process a vast number of calculations simultaneously. Classical computers, so how do they actually do, right? So I will discuss briefly about that. So classical computers works with ones and zeros. Quantum computers also in the similar way. What quantum computers are used or are called as qubits, right? Quantum bits. And then now instead of just using ones and zeros, this can use ones, zeros, and a superposition of ones and zeros. Let us see how it will be done in the next few slides, right? So then certain difficult tasks that have long been thought impossible, right? So for classical computers will be achieved quickly and efficiently by a quantum computer. So, so when we say that we have a quantum computer which can crunch the numbers fast and do lots of computations quickly and so on, then what does it mean? What is the implication of that? Is the power of quantum computer is so enormous. What cannot be done with a classical computer? Can it be done with a quantum computer? Right? So then, are there still limitations on your quantum computer? So what has been seen or looked at is that any problem solvable by a quantum computer is also solvable by a classical computer. What can be solved on a classical computer can be solved on a quantum computer, right? And then what can be solved on a quantum computer can be solved on a classical computer also. It may take nevertheless more amount of time, right? So any quantum computer can be simulated by a Turing machine. So that's what we were saying, right? So Turing machine is actually limiting something, right? Some things cannot be done, right? So if, as I said already, if a problem has no method, right, there is no way you can actually find a solution for a problem using a particular method. Then there is no way the quantum or the Turing machine can solve that problem. That's the limitation. So here, the quantum computer can be simulated by a Turing machine. That means that the quantum computer cannot solve a problem that cannot be solved by Turing machine, right? So there comes the limitation of the quantum computer. In other words, quantum computers provide no additional power over classical computers in terms of computability, right? So what we are trying to achieve in quantum computation is a speed up of the process, right? It's not that you can increase the power of quantum computer to solve the problems, right? So this means that quantum computers cannot solve undecidable problems like the halting problem, and the existence of quantum computers does not explore the Church-Turing thesis, right? So there is a limitation on what can be done, right? So then I'll briefly discuss about a few basics, and then we'll see what else we can do, right? So then, what kind of models are actually available to implement these quantum computers, right? So there are several models of quantum computers. So there are quantum circuit model, quantum Turing machine, adiabatic Turing quantum computer, one-way quantum computer, quantum cellular automata, and so on. Right? There are different models that you can use actually to implement the quantum machine, right? So D-Wave, I think it actually implements adiabatic quantum computer, right? So for the biggest quantum computer consists of maybe 100 or qubits, right? So IBM is actually proposing to build a quantum computer by 2023 consisting of some 1,000 qubits, right? So let us see what they will achieve in that time. So as has been with the classical machines, now quantum computers also they are in such a similar state. What was earlier classical machines or classical computers have been built like in a room-sized kind of space. So now quantum machines are also almost in the same stage, starting stage, right? So you require huge amount of space and huge amount of infrastructure to build the quantum computers, right? So it's not very easy to build quantum computers right now. So to produce small scale quantum computers is not going to be very easy. It may take maybe some more years to actually stabilize the systems and bring it to a small scale, that is like your laptops, etc., that are being used right now. So it's still it's not at that stage, but I think still people are kind of working on it, and then there are a lot of uh, um, um, what do you call uh, technical advancements are happening, and so we may expect it maybe in another 5-10 years to be commercially viable. So now the most important or the most widely used quantum computer is using the quantum circuits, right? So quantum circuits are based on quantum bit or qubits, which is somewhat analogous to the bit in classical computation, right? So then qubits can be in a 1 or 0 quantum state, or they can be in a superposition of 1 and 0 states, right? So then we will see what do you mean by that. And then, so the main issue or main point here is that the quantum state, right? So it can be in different states simultaneously. It is not only when you come to the classical case, you can be in one particular state. You cannot be present in all the available state at the same time, right? So that's not possible. Whereas when you go to the quantum uh, level or quantum whatever atomic level, then there is a possibility that you can be in different state. You can be present in different states simultaneously. That's the advantage of using quantum computing, right? So uh, qubit, but you can be in different states, but when you do the measurement, you cannot measure all the quantum states simultaneously. You can only actually measure one quantum state, right? They all collapse. However, when qubits are measured, the result of a measurement is always either a 0 or 1, right? So it actually collapses to the classical state when you are measuring, right? So that is the one thing that actually kind of has to be overcome in quantum computers. So the probabilities of these two outcomes depends on the quantum state that the qubits were in immediately prior to the measurement, right? So it can be in several states simultaneously, but you cannot measure all those states simultaneously. When you measure, they all collapse into one or the other state. Okay, so then how do we actually then we have to come up with algorithms that can actually uh, exploit this kind of thing, and it can actually gives us a solution for the problem that we are trying to solve. So then these qubits could be made of, right? So qubits are the bits for the quantum computers. So these qubits can be made of photons, atoms, electrons, molecules, or something else, right? So photons, atoms, electrons, etc. These are all quantum at the very small scales, quantum scale. So we have to actually then have to have system. That's the reason why right now it's not feasible to have machines at our commercially viable quantum machines, right? So to keep these photons, atoms, electrons isolated and to make them act as qubits, etc., you have to maybe you have to put them isolated in isolated spaces, and then you have to kind of keep them in their state without making jump into higher energy states and so on and so forth, right? So that requires a lot of huge infrastructure, right? So then, as I was saying, there are two principles based on which the quantum computers are built. So one is superposition, the other is called entanglement. So as we said already, what is superposition? Superposition is essentially the ability of a quantum system to be in multiple states at the same time. Right? So simultaneously, you can be present in different states. So it's for our mind, it is not at all, we cannot comprehend that, right? How can you be in different places at the same time? So I can be here, I can be in my university, or I can be in some other place simultaneously. So what does it mean? What of me will be here, what of me will be there in some other place, right? So that's very mind boggling to the brain. We cannot think about a quantum level. We know only the classical mechanics. Classical mechanics holds in our day-to-day basis. So at the classical level, we cannot comprehend that. But at the quantum level, it is possible, right? So it is like saying that I'm alive, I am dead. I can be in both states, or I am there at above, or I'm there below, right? So like that. So this is what is called the superposition. You can be in different states, right? So superposition is essentially the ability of a quantum system to be in multiple states at the same time. That is, something can be here and there or up and down at the same time. Right. So, okay. So you know that you can actually have your system in different states. Now, how do you build the quantum circuits? Quantum circuits are based on quantum bits that are qubits, right? So qubits can be in different states simultaneously. And yeah, so this we have seen already. So So when you look at, right, so a classical bit can be in a state when the voltage is close to zero, it is said to be state zero, and the voltage is high, about 5 volts maybe. Then we say that the whatever pixel or whatever, or we have the state of the transistor is in a one state one, right? So either it can be in state zero or it can be in state one. It cannot be in both states simultaneously. Whereas a quantum bit, a qubit can be state zero or one, or it can be a combination of zero and one. Right? It need not be 0.5 all the time, probability. So classical bit, if you take a 3-bit system, let us say, it can be in 8. The possible states for 3 bits is 8, right? 0, 0, 0, 0, 1, and so on. So maybe it can be present in only one of the state, depending on how the bits are set in a system, right? So 101, or it can be 00. Whereas a quantum bit, it can be simultaneously in present in all the 8 possible states. If you take 3 quantum bits, then it can be present in all the 3 possible states. So that's the difference between the classical and quantum scenarios. So same thing as a picture here. So and a classical bit can be a 0 or it can be 1, right? So when you look at n number of bits, then there are 2 power n possible bit patterns that are possible, and the system will be in one of the 2 power n possible permutations, right? So it can be in any one of the state, but it can be only one state, right? So whereas quantum bit, it can be in all possible 2 power n states, right? So then how actually this is possible? Okay, so how is that it can be in all possible states, and how it can be done? So this comes from actually the wave particle duality of the electrons or atoms and so on. Even molecules can exhibit this, right? Not the higher bodies, right? So the heavier bodies don't exhibit this phenomenon, but the smaller particles, they exhibit this phenomenon. So we all have studied, right? So light can exhibit this wave particle duality, right? So it can behave like a wave in certain situations, or it can behave like a particle in certain situations, right? So that is what you call as wave particle duality. So then the same simple thing here is that, let us say if you have a source emitting single photon, then you have a beam splitter, then the wave or the energy, photon is basically a unit of energy. The energy that's coming, it can be split. Some will be transmitted in horizontal direction, some will be reflected along the v direction. So if you put the receptors at these ends, then there is a probability that you will get 50% that you will detect it, right? Either at receptor A or at the receptor B. Right. So then there is one more experiment that actually now the same beam is coming. There is a half silvered beam splitter. Then the beam splitter actually splits the beam into horizontal vertical directions. And then these are fully silvered, so they will just reflect whatever is coming to them. And then it goes to the again one more beam splitter, and there are two receptors A and B. Right. So very amazing thing that happens here is that what is the probability of observing the beam at A and B? Right? So the probability of observing A is 100%. The probability of observing the beam at B is 0%. Right? So what is the meaning of that? Right? So scientists have conducted one more experiment where they try to block one of the paths, right? So when they try to block one of the paths, then it so happens that the beam, you can detect it B. So what is happening? How is that the energy that is being transmitted or reflected along different directions, right? So then what is happening when you are blocking the thing, right? So when you are blocking, how does it know that there is a block? So it cannot take that path, and then it has to come through some other path and it will reach the receptor B, right? So for it to actually see and understand that there is a block is that it travels to one of the paths and it travels to the other path also, and then only it will actually kind of understands that there is a block, so it cannot proceed further along that block, and then it comes to the other block. So what is the time that it takes is the same, right? So it actually proves that the beam is actually split and it is going through different paths, going along both path A and path B here, right? So it means that this is what actually we are saying. It can be in both, whatever is the number of states, right? It is simultaneously in state 0, state 1, or it can be in the superposition of state 0 and state 1, right? So that is what we are meaning by saying a superposition, right? So unless it knows that there is a block, it cannot be reaching the receptor, right? B. So how does it know that there is a block? Is that unless it travels to all the possible paths, then only it will know that there is a block, right? So it means that the same thing is being split into horizontal and vertical direction, and then it is reaching, actually trying the possible paths that are there, and then it is actually understanding that there is a block, right? Unless it is doing both of them simultaneously, that is not possible. So that's the main thing behind superposition here, right? So this wave particle duality, that superposition is what is being used in the quantum computers. So how do you represent this data, right? The superposition, right? So single qubit can be forced into a superposition of the two states, right? Denoted. So this is a mathematical denotation. Alpha 1 and alpha 2 are called quantum amplitudes, and mod alpha 1 square, the probabilities, total probability is equal to 1. Alpha 1 square plus mod alpha 2 square is equal to 1. And then what is the probability that is being in state 0? What is the probability of being in state 1, right? So that is what we are using for the qubit here, right? So we get probability of state 0 mod alpha 1 square and probability of 1 is mod alpha 2 square. So each qubit can be in both states 0 and 1. That's how you are having, when you have n number of qubits, you have 2 to the power of n minus 1 states, right? 0 to 2 power n minus 1 states simultaneously. It can exist in 2 power n states simultaneously. That's what you mean by the superposition, right? So this comes from the property of the, or the nature of the particles at the quantum level. So the other property that is used in quantum computers is called quantum entanglement, right? So entanglement is, they are put together, right? So the observation of correlation among various events, right? So we can observe correlations in various ways. So this entanglement is an extremely strong correlation that exists between quantum particles. Quantum entanglement allows qubits that are separated by incredible distances to interact with each other, right? So however far they may be put, they can interact with each other simultaneously. So that is called a quantum entanglement. This kind of correlation is very strong, right? So no matter how large the distance between the correlated particles, they will remain entangled as long as they are isolated, right? So taken together, quantum superposition and entanglement creates an enormously enhanced computing power. So one qubit, then you can have multi-qubit, more than one qubit acting together, right? So qubits in a multi-qubit system, they are not independent. They can become entangled, right? If you measure both bits, so if you take now 2 bits instead of, let us say, 1 qubit, so then it can be simultaneously in the state 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 possible states, given 0, 1 as the thing, right? So then there is a possibility that it could be in state 0, 0 or 0, 1, 1, 0 or 1, 1. In classical scenario, it can be only in one of these states, right? So whereas in quantum, it can be in all these states. It can be present in all these states. So we get x, y. So this is a bracket notation that you are using for denoting the state 0 and state 1. So x1, y can be in a particular state with the probability alpha xy square. So then, yeah, so how do we actually have materials that actually can act as qubits, right? So what is the technology that is available? So of late, nanomaterials are being used hugely in various applications, right? So then these nanomaterials are actually useful in actually building these kind of qubits, right? Physically, we want to build the qubits. So how is it possible that we can get these qubits? So if the size of a material is comparable to its Compton's wavelength, then it exhibits nano property and the materials are called nanomaterials, right? So this is found to be an order of 10 power minus 9 meters. This is the reason why these materials exhibit nano property, right? So in nanomaterials, there is a reduction of degree of freedom to 2 or lesser dimensions, right? So the uses of nanomaterials in the manufacturing of computers justify the Moore's law, right? So Moore's law is about doubling the power of the computer every 18 months. So how do we double that? If we can actually pack more and more number of computing elements, then the computing power goes up, right? So if you want to pack more and more computing elements, then the size of the computing elements has to become smaller and smaller, right? So when it becomes smaller and smaller, there is a huge probability that a lot of interactions can go between them, then corrupt the systems, right? So now, in order to avoid that, now you can take or make use of um, nanomaterials, right? So quantum wells are one of the three basic components of quantum devices that are ultra-thin quasi 3D planes. An arrow strip sliced from one of the planes, right, is a 1D quantum wire. Dicing up a 1D wire yields a zero-dimensional quantum dot. Reducing the number of dimensions in this manner forces electron to behave in a more atomic-like manner. Right? You are restricting the degree of freedom for the electron. So then you can actually make quantum dots using these zero-dimensional entities, which have practically no degree of freedom. Hence, their interaction with the environment is also ideally zero. Right? So it is ideally zero. So it means that in practical situations, it may not be ideally zero. So they are very kind of uh, uh, unstable in a way, right? So there may be a lot of the noise or anything can actually make them actually decay into some other thing, right? So the noise, they can be actually interacting with each other and then corrupting the signal. That's the thing. The stability of the system is very crucial to maintain. So otherwise, the whatever systems that we are building, right? So they are not stable, and then there is no way that actually you can make them work and you can make them deliver the results, right? So if you look at the atomic force microscope, this is how the quantum dots can be seen, right? So these quantum dots, essentially they are qubits, okay, the quantum bits. So these quantum dots in turn can be used to construct the quantum gates, and these quantum gates in turn can be used to construct a quantum circuit, right? So these quantum circuits, building up quantum circuits is one way of actually realizing the quantum computer. There are different ways of realizing the quantum computers, right? So using quantum dots is one of the ways. So the quantum gate, how do you construct the quantum gate? Conventional logic gate, we all know Boolean algebra, right? A NOT gate is, if you give input as yes, it will deliver output as no, and if it is a no, it will be an yes, right? A quantum logic gate is yes, it will give 50% chance of yes or no. Right? If you say yes as the input, then there is a 50-50 chance of getting a yes or no. Similarly, a no as input will give you a 50-50 chance of yes or no. Right? So that's the nature of your quantum circuits, right? Or quantum gates. So fine. So the other ways of realizing the quantum computers in addition to quantum dots is heteropolymers, right? So in this, a linear array of atoms is used as memory cells, and then ion traps, energy states of ions is operated by this, right? And then quantum electrodynamics cavity, a QED cavity filled with some cesium atoms, and an arrangement of lasers, phase shift detectors, polarizer, and mirrors. Right? So first of all, you have to have something that can act as a qubit, right? So then you need to have an operators actually that can um, manage these qubits, right? So nuclear magnetic resonance, a capsule filled with a liquid and an NMR machine, Josephson junctions, a Cooper pair box, which is a small superconducting island electrode, which is weakly coupled to a bulk superconductor, right? So it forms a Josephson junction between these two things. Kane computer, it uses a single magnetically active nucleus of P31, right? And topological quantum computers, which uses anions, right? So you could be using any one of these to get your qubits, and then you can construct your quantum computers. So the basic implementation of a quantum computers requires first the qubit implementation itself, right? So how to build the qubits, right? What kind of qubits? Is it anions or is it ion traps, quantum dots, or P31? Whatever is the thing that you would like to use for qubit implementation, right? So then control of unitary evolution, right? How they entangle with each other, and you also require to um, prepare the initial state of the qubits. So what are the initial states for the qubits? And then you also need to have a measurement of the final states, right? So you have qubits and you have to initialize the qubits, right? And then you have to measure what is the output of the qubits, right? So, okay. So briefly, what are the kinds of applications that you can come up with quantum computers, right? So wherever you have huge number crunching, huge computations that are there, all those places you can use your quantum computers, right? Artificial intelligence and machine learning, obviously, right? So we are right now we are into the deep learning more and more to learn things, the representations without, we don't want to give the features by ourselves, but we are asking the machine itself to learn the features. What are the things that actually are essential for the application, right? So quantum computers can help in that, and computational chemistry, the number of atoms in a particular what do you call the material, right? So what is the, how do you actually to predict the structure, right? How what is the placement of the atoms and so on. So that is a huge field that can be using, that can use the quantum computers. Drug design, obviously, right? So it's we know that because of our COVID situation, that it requires a lot of time to design drugs and test and so on, right? So actual cycle of the developing a drug may take something like more than 6 to 10 years, right? So a lot of that is because of the designing that we have to come up with to suit a particular disease or particular thing, right? So in order to do that, then you have to compute a lot of things, right? The structure of the um, protein structure of the molecule that we are designing to use as a drug, right? So all these also very computationally intensive applications. Then cybersecurity and cryptography, yeah, cybersecurity and cryptography mostly they are dependent, or mostly they are the most what do you call popular is the RSA algorithm. So RSA algorithm is mainly dependent on factorization problem, right? So once we are having this quantum computers, then your RSA will be no longer effective, right? So factorization, which takes exponential time using the classical computers, actually can be done in polynomial time using the quantum computers. So then comes the question of how do you improve the cyber security, how the security has to be improved, and how actually you can maintain your security still, right? In the face of having quantum computers which can crunch the large numbers very easily, right? So each of them requires an algorithm, right? How to use it. So quantum computer is like your classical computer. It has certain power. How do you harness that power is up to you, right? What kind of algorithm you can write to harness that power is what you have to come up with. Financial modeling, stock markets, and etc. and so on. Weather forecasting. Weather forecasting is very complex system, right? So then accurately predict the weather. Then how do you use this to do that? So that is your weather forecasting. Logistics optimization, any optimization problem requires, right? So optimization problem as such is an NP problem, right? So then even if you kind of specify what is the criteria that you need to hello. Okay, right. So what is the what is the optimization problems require exponential, or they take up exponential amount of time. So you have to actually give how much you have to actually then come up with the best solution in optimization problem. So I will briefly go through this Shor's algorithm, which is an algorithm that's used to do the factorization. So the main idea behind the Shor's algorithm is that it uses modular arithmetic, and it uses quantum parallelism, and it also uses quantum Fourier transform. Right. So it is basically that given a number, right? In RSA algorithm, it is given you have to find two prime factors for the key, right? So then how do you find the prime factors for the key? That is your factorization problem. So then it will actually using the modular arithmetic, where we can see, let us say if you are given the number 15, and you can start with any number 1 and so on till the number n, and then you give x equal to 7 and so on. You assume x equal to 7, then you are computing 70 mod 15, 71 mod 15. So we can see that there is a periodicity here, 17413, 17413, like that. The periodicity will be there. So you have to capture that periodicity here. Okay, there is not enough time to go through the entire thing. So when you capture this kind of periodicity here, like 17413, 17413, so the input registers are there. So then the output register is there. So output register can be, because this is 15, though there are 3 qubits there in the output register. Then the input register, we have taken q value, some q value as 255. You have to take q value large so that you will have more probability of that. So this periodicity, what is the periodicity here? You have to capture simultaneously, right? So then we take the measurement on the output register. This will collapse the superposition to represent just one of the results of the transformation, right? So output, the system can be simultaneously in all the possible states, but the output, when you want to measure, it can be measuring only one state. So this one state actually collapses the input also, input registers also. This is the entanglement that we have been talking about. Whatever output that we are measuring, that also collapses the input here, right? So maybe we are measuring periodicity of 1. So periodicity of 1 occurs at 1, 4, 7, and 13, right? So we will be measuring what is the periodicity here. So in order to measure this periodicity, you will be using the quantum Fourier transform here, right? So quantum Fourier transform actually measures the periodicity. So you will be using the quantum Fourier transform for that. So you will be getting whatever is the probability, or whatever is the periodicity of that. So once you get the periodicity, then you will put x power p by 2, right? Periodicity p by 2 plus 1. So we have taken example as 7. So 7 power p by 2 plus 1. So this is the GCD of the thing. So equal to 5, and GCD of 7 p by 2. Sorry, this should be 7 power p by 2 minus 1 comma 15 is 3. So that's how you can actually get what are the factors for the number. So this actually captures the periodicity of the repeating pattern, and then it actually captures that. So all these measurements, 7 power 0, 7 power 1, and so on, all these things can be measured simultaneously. That's why the complexity actually comes down to the polynomial, right? So quantum decoherence is isolating the system from the environment, as interactions with externals would cause the system to decohere, right? So some quantum computers require the qubits to be cooled to 20 millikelvins in order to prevent significant decoherence, right? So finally, computability, right? Any problem solvable by a computer, quantum computer is also solvable by a classical computer, right? So the complexity class of the quantum computers is called BQP, right? Bounded array quantum polynomial time. So BQP is it's not proven that BQP is kind of is a superset of your NP complete. So that's the reason why still there is no um, guarantee that we can solve the NP complete problems using the quantum computers, right? But we don't know what future advancements will bring us. Fine. Yeah. So I will stop the lecture here. Sorry, I couldn't complete the entire thing. And if there are any questions, I would like to take them.
Thank you, ma'am. Are there any questions from the participants? Ma'am, I'll go ahead with the vote of thanks.
Yeah.
Ma'am, you started. Your lecture was really very simplified. I mean, we were like down to earth, ma'am. We thought, ma'am, quantum mechanics will be very tough. I don't know, but you made it very simple. It was very clear to the beginners. I myself treat my as a beginner, and I was able to correlate with the things. It was very nice, ma'am. I would like to focus on the things that I have noted down from the lecture. You started with explaining the limitations of the classical computer model and the need of having a parallel system, and then you introduced us about the Feynman and the Schwartz models and how they are using quantum mechanics process in building a quantum computer. You introduced us about the classical computer codes that with the way you write the data in terms of 0 and 1, and the advantage of having quantum computers having writing the information in terms of 0, 1, and superposition of zeros and ones. And in thus we were introduced to quantum bits, that is qubits. Then we were also introduced to several quantum computing systems, multiple things you have introduced us. And but as a mathematician, I was little bit searching for the mathematical approach, and there you discussed about quantum amplitudes with the help of the vectors. And what the present nanomaterials that is used in quantum computers will enhance its functioning was spoken. And then quantum dots seen with the atomic force microscope was also very encouraging, ma'am, to see it. We were talking and we were discussing, but seeing it in a pic was really, and I mean, we were motivated to learn more about it now. And you spoke about the Moore's law. As a mathematician, I know, but I was not into the subject. But really, ma'am, you have enhanced our learning. You have enlightened our approach in the quantum mechanics. At the end, you spoke about the applications in artificial intelligence and machine learning, drug design and development, weathering forecast, and many more. Ma'am, it was really an enlightening talk, ma'am. We want to hear you more and to learn and grow. Thank you. Thank you, ma'am.
Thank you very much.
Raj Reddy, sir?
Madam,
Yes, sir.
Madam, thank you. All the way you came and delivered the lecture. It is really, because where you have to start, where you have to end, because it is a quantum computing is nothing but it is a combination of mathematics, physics, electronics,
Yeah.
computer science. But you covered particle theory to nanoparticle theory, then in between the circuits and all. So your lecture is enlightened, madam. Thank you very much. All the way come over and deliver the lecture.
Thank you very much for inviting also.
Thank you, madam. Thank you.
So can I exit?
Yes, ma'am.
Yeah.
Yes, please.
Thank you very much. All the best for the program.
Thank you. Thank you, ma'am. I request all the participants to go for a break of 15 minutes. We'll again join for the second lecture at 10:45 with the same link.